Good morning, all. Am I audible?
Yes, sir.
Okay. Okay.
One.
Thank you, sir. So before I start today's class, just I want to convey my gratitude for organizing such a nice program on 5th September. It was very well conducted, and Kausar's anchoring was very good. So one thing I want to request Movoni. So due to some urgent work, I missed the googly round, but later on I heard that it went very well. So I'll request you, if possible, if you can share the questions, then it will be very good. Okay. Due to some urgent work, I missed that part, but later on I heard that it was very good. So that's why I'm requesting you, if possible, if you can share it with me, then it will be very fine, very good.
Sure, sir. Thank you.
Okay. Okay.
Yes, sir. And Pubarun also deserves the credit because the whole planning was his idea. I helped
Okay.
him plan and I anchored, but it was his idea to begin with.
Okay. Purbarun was the backend instructor. That's so actually
Yes,
we
he
actually see
came up with
those
the
people
proposal.
who come forward actually, but besides that, there are lots of people who actually execute that plan. So we don't find them directly, but they are the main pillar of conducting such a nice conducted event. Yeah. Thank you, Purbarun.
Thank you, sir.
Okay. So just I want to sum up whatever I have discussed so far. So in the last class, I have started discussing the limit. And okay, so before that, I want to ask one more question. So I think all of you have got your last semester's result. I think all of you have got good marks, no? Are you all satisfied with the marks that you have got?
Yes,
I
sir.
am.
Okay. So is there anyone who wants to change the stream? Because after 10 or within 10 or 15 days, perhaps the notice will be given. So based on the previous two semesters CGPA as well as the vacancies in the department where you wish to go, you can actually apply for those stream change. But obviously, I hope you will be here. You will be in the mechanical department so that I could actually communicate with you all. But if you desire to change the stream, then within 10 or 15 days perhaps the notice will be given. Okay, so in the last class I have discussed the limit, how to find out the limit and how to verify whether limit exists for a particular function or not, and I have discussed also the continuity. So also you can see in the Google Classroom I have shared the first class note related to the function of complex variable. So the class note is actually given up to differentiation. So apart from the class notes theories or problems, I have given some problems also, some examples also where the problems are unsolved. You can solve those problems. So if you face any kind of difficulty in solving those problems, you can ask me in next class, because I don't think you have gone through the overall class note. So just go through it once, and if you try to solve the problems which are given over there. So if you face any kind of problem in solving anything, then the next class, of course, you can ask me. So I'll try to solve those problems. So today I'll start the differentiation. Okay. So just let me share my screen. Can you see the blank screen?
Yes, sir.
Okay, thank you. So today we'll discuss the differentiation of a complex valued function. Differentiability of a complex valued function. So before we could proceed towards the differentiability of a complex valued function, just like the limit, continuity, whatever method I have followed, I will be following here also the same thing. So before discussing the differentiability of a complex valued function, just I want to focus on the differentiability of function of one real variable and two real variable, as you have studied this earlier. So whenever we'll be discussing this, and after that we'll be discussing the differentiability of function of complex variable, then I think you will be able to correlate the previous knowledge with the thing that we will be studying here right now. So first, if we consider the function of one variable y equals to fx, so can anyone tell me what is the significance of doing the differentiation? So here you know that we find the derivative of y with respect to x, that is denoted by dy dx, or we find the derivative at this also denoted by f dash x. So at a point x equals to x0 if we find, so this will be f of x0. So what is the significance and why do we differentiate a function? Can anyone tell me? Already have studied this in class 11, I guess. So
Sir, for finding the slopes.
for finding the slope. So what we will do by finding the slope? What is the significance of finding the slope?
Sir, to determine the maxima minima.
Yeah, this is one application we can find the maximum minimum. So apart from this thing, can anyone tell me what are the other significances? Lots of significances are there. So apart from finding the slope, can anyone tell me?
So, like practical applications, there is instant velocity.
Yeah, instant velocity also you can find. Yeah, so lots of applications are there. So differentiation means that this is a function that is y equals to fx. So if a point is given to us, that is say x0, so we can draw the tangent at this point, and the slope of the tangent is denoted as f dash x at the given point. So if this is x0 point, so actually what are the significances of doing the differentiation? So there are two major significances. One is, let's say we are considering one car, and let's say one particle is moving along this curve, that means along this closed curve or along this circular orbit. So at any instant, if we want to identify its direction of rotation or direction of movement, then we can find the direction by virtue of the tangent. So if it is here, then this is the direction of that particle. If the particle is here, so this is the direction of the particle. So if a particle is moving, if I consider this path, so if a particle is here, then the direction will be along this. If a particle is here, the direction will be along this. So if a function is differentiable and a particle follows that path, to traverse from some point to another point, then at any instant we can identify what is the direction of the movement of that particle through drawing the tangent. So this is one significance. Another significance is that let us consider a system. Okay, system means say any system we can consider. Say in mechanical system you can different system you can consider. So you know that lots of inputs are there with respect to which the system is dependent. Say for example some independent variables are there depending on which we can vary the dependent variable. So say for example if we measure the value of the system at a particular for a particular variable, say 150, then if I vary the independent variables, that means depending on which the system is getting changed, then depending on the values of independent variable the system will be changed. But if we want to measure the gross change, so that will be very much problematic. We will not be able to identify what is the total change in the system that is occurring. So that's why we need to find out the rate of change. That means if the dependent variable is y, say for example population of our country. So if we want to measure the population of our country, lots of factors are there depending on which the population increasing or decreasing. Say for example the weather, the environment, the socio-economical condition. So lots of factors are there. So if I want to identify that population is 130 crore and next 5 years population is 150 crore, next 2 years population is 165 crore, then we can identify what is the gross population. But if we don't identify what is the rate of change of the population, then it is not possible for us whether there is a growth in the population or there is a decay in the population. That means whether it is getting changed time to time, that means it is increasing, but whether the growth of population is increasing or not, so that we can measure directly by this gross amount. So for that we need to know the rate of change. So if the independent variable is y, say for example depending on the socio-economical condition, depending on the literacy rate, this population is total population is increasing. So if I want to measure the rate of change of one dependent variable with respect to the independent variable x, that we can do by doing the differentiation. So that two are major applications of differentiation. One is we can identify the direction of a particle that is moving along a path by virtue of drawing a tangent at a given point, as well as if I consider a system, then we can measure the rate of change of the dependent variable with respect to the independent variable by virtue of doing the differentiation. Now you know that why we can do so, because that lies from the definition of tangent. So what is how we can define or how we can derive the tangent? So for that, all of you know, we know the first principle. First principle means if this is a point where we want to draw the tangent, so we'll be changing this independent variable little more, or we'll be considering a small increment with respect to this independent variable. Let's say this point is x0 plus del x. So if this curve is y equals to fx, so these 2 points, if I draw the perpendicular, then these 2 points will be on the curve. So the coordinate of this point will be x coordinate will be x0 and y coordinate will be f of x0. And for this point x coordinate will be x0 plus del x and y coordinate will be f of x0 plus del x. So if I want to draw the tangent over here, for that we'll be joining these 2 points through a chord. If this chord makes an angle theta, then you know that this angle will also be theta. Now tan of theta is, for this triangle, will be base height by base. So what is the length of height? So this ordinate is actually f of x0 plus del x, and the length of this ordinate is f of x0. So difference between these will be the length of this amount. That means f of x0 plus del x minus f of x0, and the base will be, this total length is x0 plus del x, this length is x0, so this length will be del x. Now whenever this point will move towards this point and will coincide, then only this chord will be converted to a tangent. That means if this point moves towards this point, then this distance will be gradually coming towards 0. That means this will be coming closer to this point, so this length will be actually converting towards 0. So that means limit del x tends to 0, this is actually tan theta or dy dx or f dash x. So here, while we are considering this quotient, in the denominator you can find that this is the change in dependent variable f, and this is the change in independent variable. So in that way we can measure the rate of change of dependent variable with respect to the independent variable by virtue of drawing a tangent. So this is the major significance, and this is called the first principle. Now whenever you have studied the function of two variable, let's say, so z equals to f of xy. So here, since number of independent variable are 2, so if we want to measure the rate of change of the dependent variable z by simultaneously changing x and y, we can measure whose impact is more on z. So that's why if the number of independent variable are more than 1, so in the previous manner we won't be able to find out the rate of change of the dependent variable with respect to independent variable directly. Rather, here we need to consider the rate of change of the dependent variable z with respect to the independent variable x by keeping y constant. Otherwise, if we change both x and y, then we won't be able to identify whose impact is more or whose impact is less on z. So instead of the ordinary derivative, this is denoted as del z del x. Similarly, we can measure the rate of change of z with respect to y, keeping x constant. So if I consider more than one independent variable, so instead of ordinary derivative, there will be two partial derivatives. You know, all of you are familiar with that. You have studied this in first semester. So now we will be discussing what is the significance of this partial derivative. So you know that whenever we are considering the function of one independent variable, then we can measure the rate of change of y with respect to x. So the angle that is made by this tangent with respect to the independent axis, that is x axis, that is measured with respect to this derivative. Now here there are two partial derivatives. So whatever we are going to measure, or what is the geometrical significance? So let us consider a three-dimensional plane, xyz plane. So the independent axis is here xy plane, not x axis, and this is the z axis, the dependent axis. So we are considering a surface. Now you know that if I draw, whenever we are considering a vector valued function or vector valued vector, then you know that we can find the component of this vector along the coordinate axis. Along x axis we can get a component, along y axis, parallel to y axis, we can get a component, and the resultant of these two components will be actually the main vector. So similarly here also, since we are actually drawing a tangent at a given point, so the tangent will lie in xy plane, since this is a three-dimensional reference frame. So here the tangent will not be a tangent, rather it will be a tangent plane. I don't know whether you have heard this in the first semester, because in first semester in the multivariable calculus it was there, the tangent plane. So instead of the tangent, here we will be getting the tangent plane. So if I consider the core of the tangent plane, that means a vector, the tangent plane has a particular direction. So if I consider this as a vector, so we can segregate this tangent plane in two components. One is parallel along x axis, one is parallel along y axis. So this is called as the del z del x, and this is called as the del z del y, and this is called as the del z del x. So the tangent plane, the direction vector of the tangent plane can be segregated in two parts or two components. So one component is parallel along y axis, another component is parallel along x axis. So they are called as the partial derivatives del z del y and del z del x. So these are the significances of the partial derivative while we are considering function of two real independent variable. Was that clear? Was that clear or not? Have you understood this?
Yes,
Yes,
sir.
sir.
Now we will be discussing what is the significance of the differentiability for a complex valued function. So let us consider fz as a single valued function of z in the domain D, and fz is differentiable at z0. That means here the definition will be same. The independent rate of change of dependent variable fz from z0 to z0 plus del z divided by change in the independent variable, that is del z, whenever limit del z tends to 0, that is denoted by f dash z0. So what is the significance? So here we know that since we are considering here the function of complex variable fz equals to w, so z and w being two complex numbers have real and imaginary part. So z has real part x and imaginary part y. Similarly w or fz has real part u and imaginary part v. So since there are total 4 variables, 2 independent and 2 dependent, so unlike the function of 2 real variables, here we won't be able to consider all those 4 variables in a single frame of reference. So that's why you know that here we need to consider the independent variable in the z plane, z argon plane, and we can consider the dependent variable in w argon plane. So let us consider one point z0. So if I consider a complex valued point or complex point, then you know that in Argand plane that represents a two-dimensional point. So Z0 has a real part x0 and imaginary part y0, and that is denoted by P. So you know that if I consider any point in two-dimensional plane, then we can consider a positional vector to identify that point. Positional vector means the vector that is directed towards its point and that originates from origin. So this is the positional vector of P. P is nothing but the point Z0. So if I consider a small increment with respect to Z0 in that direction that is perpendicular to the positional vector P, so that amount is very small, that is del Z. So you know that if I consider the vector and if I consider a triangle, then if two sides of a triangle represents two vectors, then the third side represents the resultant vector. So similarly here, this is Z0 and we are considering a small increment along the perpendicular direction of the positional vector of Z0. Then this coordinate will be obviously Z0 plus del Z. So that is identified as the point Q. So P is a point we are considering which is denoted by Z0. So we are considering a small increment in the perpendicular direction of P, that is del Z. Then we are getting the resultant vector, positional vector Z0 plus del Z, that is identified by the point Q. So we know that whenever we are defining the function fz, so each and every point that we are considering in the independent plane z will be mapped to the dependent plane w. So here p will also be mapped to a point in the w plane, that is p prime. So the coordinate of p prime will be fz0, since this is the image of z0. So that is identified at w0. Similarly, q will also be mapped to a point q prime. So q prime is the image of q. So that will be f of z0 plus del z. Now, if we can join p prime and q prime by a vector quantity, so that will be obviously by the triangular law will be fz0 plus del z minus fz0. Now, the quotient of p prime q prime divided by pq will be considering, and whenever p prime comes closer to q, then p will come closer to q, that means del z will be 10 to 0, then p prime will also gradually come to q prime. So that is the significance of differentiability. So if the limit of this quotient exists, then only we will be saying that the function is differentiable at z0 and will be denoted by dash z0. Otherwise, it is not possible for us to evaluate the derivative of that function at the given point z0. Was it clear? Was that clear or not?
Yes, sir. Clear, sir.
Then we will be discussing the properties of differentiability. So, sorry, I have mistakenly written here continuous. It will be differentiable. So, if two functions fz and gz are continuous at a point z0, differentiable at a point z0, then their sum and subtraction of two functions will also be continuous at z0, and this will be denoted by d dz of fz plus minus gz will be d fz dz plus minus d gz dz. Similarly, the rules are same. Whatever we have studied earlier, the same rule will be adopting here also. So if two functions fz and gz are differentiable at a point z0, then their product will also be differentiable, and the derivative of the product will be gz will be constant, derivative of fz plus fz will be constant, derivative of gz. Similarly, if two functions are differentiable at a given point z0, then their quotient will also be differentiable and will be denoted as this. So it will be defined provided the denominator, that is gz, is not equals to 0. So then we will be discussing how to check whether a function is differentiable or not. So for that we can adopt actually the first principle that we have discussed here, because you know that in class 11 also to verify whether a function of one real variable is differentiable or not, you have used the first principle. So here also we need to use a similar kind of definition to check whether a given function is differentiable or not. So the function is given as fz equals to z bar. So here no particular point is mentioned. So that means we need to check the differentiability of the function with respect to any arbitrary complex number z. So by definition, fz z equals to limit del z tends to 0, f of z plus del z minus fz by del z. So if this limit of the quotient exists, then only we will be saying that the function is differentiable for any arbitrary point z, otherwise we will say that the function is not differentiable. So since we are approaching towards the path del z tends to 0, then del z can be written in the form of z is x plus iy. So del z will be del x plus I del y, because the complex number will be increased if the real part is increasing as well as the imaginary part is increasing simultaneously. So f dash z will be limit del z tends to 0. So f of z plus del z. So if z is z bar, so z plus f of z plus del z will be z plus del z bar minus z bar if z is z bar by del z. So if this will be del z tends to 0. So del z has the real part x, imaginary part y, del y. So this will be limit del x del y tends to 0 0. Z means x plus iy, del z means del x plus I del y minus x plus iy bar by del x plus I del y. So you know that x plus iy bar is x minus iy, del x plus I del y bar equals to del x minus I del y minus of x minus iy. So x iy will be deducted. So ultimately it will be converted in that form. So now to verify whether the limit of this quotient exists or not, so we need to consider two arbitrary paths. First we need to check whether we can disprove it, that means whether we can prove that the limit doesn't exist, because it is easier, because we can adopt any two path or a family of path. If the limiting value is dependent on path, at once we can say that the limit doesn't exist. If we can't prove so, then we need to verify by epsilon delta definition that I didn't discuss so far whether the limit exists or not. So first we'll try to disprove it, that means we try to prove that the limit doesn't exist. So if we want to approach towards the origin, so infinite number of paths are there through which we can approach towards the origin, but two important paths we can follow, that is very obvious. One is the x-axis, one is the y-axis. So through x-axis we can approach to 0 0 origin, through y-axis also we can approach to the origin. So here we are approaching towards the x-axis. So if we want to approach towards the x-axis through the x-axis towards 0 0, then the coordinate of value of y will be 0, so del y will be 0. So the limiting value will be dependent on x only. So limit del x tends to 0, del x by del x, so that will be 1. Now if we want to approach through the path of y-axis towards the point 0 0, then through y-axis if we want to approach, so del x will be 0. So del x will be 0 means the limiting value will be dependent on y only. So that means limit del y tends to 0, del x is 0, del x is 0 minus I del y by I del y. So this is minus 1. So here whenever we are approaching towards the origin through x-axis, we are getting the limit as 1. Whenever we are approaching towards the origin through y-axis, we are getting the limiting value as minus 1. So here the limiting value are coming different whenever we are following two different paths. So that's why at once we can say that the limit of this quotient doesn't exist. So since the limit of this quotient doesn't exist, so at once we can say that the function is not differentiable for any arbitrary point z whenever the function is defined as f z equals to z bar. Was that clear?
Yes, sir.
Then I have given you some problems. I have shared already this note in the Google Classroom, so you can verify, you can try to solve this problem, and if you can't solve, in the next class you'll be asking me, I'll be solving this. Okay, so this is one problem. Okay, then we'll be discussing one important property or important concept, that is called as the analytic function. So the concept of analytic function is only valid function of complex variable. So this is not valid for function of one or two real variable. Why this concept is so important? So let us consider one simple example. I have given you three functions of one variable. So y equals to sin x, y equals to mod x, and let's say y equals to x square. I'm asking one question, that just tell me whether these three functions are differentiable for any real number. That means if I take arbitrarily x0 as any real number, then how you can say whether these three functions are differentiable for any arbitrary real number or not? How to answer this? So three functions are given to you, any specific point is not mentioned, so altogether the set of real numbers is given, and you are asked to check whether these three functions is differentiable at any arbitrary real number or not, at any arbitrary real point or not. And how we can proceed? Have you understood my question?
Hello, sir. From graph we can say, sir. Hello, sir.
But if
Hello, sir.
here the functions are very easier, so if the functions are very complicated, you can't draw the graph, then say if I give you these functions here, y equal to x cube sin x. So by graph you can obviously answer if you can draw the graph easily.
Hello, sir.
Yeah.
Sir, we can check one principal domain for sine from 0 to pi. And there,
So forget about sine. If I give you arbitrary function, any function, not very simple function, y equals to fx, this function is given. Arbitrary function. And you are asked to answer whether this function is differentiable at any arbitrary point or not. Any answer coming to your mind? Okay, what you need to do, if an arbitrary function is given to you and you are asked to check whether this function is differentiable for any arbitrary real number or not, then what you can do, you can check, you can consider any x0 as the arbitrary real number, you can check whether this limit exists or not, because you need to check the derivative point wise. That means if you can consider any arbitrary point as a real number, you can actually derive it. If this is defined for any arbitrary value x0, you can say that the function is differentiable. Is that clear or not? Because if you put x square here, then it will be coming as 2x0. So since if I take any arbitrary value of x0, 2x0 will be always defined. So then we can say that this derivative will exist for any arbitrary real number. So I need to take point wise. I need to check without by using this definition. Without using this definition, I can't say whether a function is differentiable at that given point or not. Is that clear? Is that clear or not?
Yes, sir.
But for complex number, if I know that the function is analytic, then it is very much easier for us. We don't need to check the differentiability of the function point wise. So what is the definition of analytic function? If I consider that a function fz is analytic at one complex number z equals to z0, that implies fz is differentiable at z0. Not only that, but around the point z0 we can construct any arbitrary neighborhood, because neighborhood means you know that a neighborhood is not unique. We can take any radius around that point by considering this point in the center, then we can construct any neighborhood. So if the function is analytic, then not only this function is differentiable at z0, but at all the points which are there inside this neighborhood, the function is differentiable. So if I know that the function is analytic at z0, then it gives us the assurance that the function is differentiable at all these points. So if I know that the function is analytic, so at infinite number of points which are enclosed within a neighborhood of that given point, we can provide the assurance that the function is differentiable. We don't need to check it separately. Is that clear? So later on I will be discussing how to check whether a function is analytic or not. But if a function is analytic, then we will be able to know whether the function is differentiable in all the points enclosed within a neighborhood, that we can construct considering the given point in the center.
Hello, sir.
Yeah.
Sir, how will know that that it is a analytic function or
Yeah,
not?
that I will be discussing later. But definition of analytic function is this. So how to check whether a function
Okay.
is analytic or not, I will be discussing. Obviously, there is some theorem by which we can actually check whether a function is analytic or not. So then here compared to, so this is broader concept compared to the differentiability of function, because while we are considering the differentiability of a function, we are considering the differentiability of derivative only at a given point, but it ensures the differentiability in all these points within a neighborhood of a given point. So compared to this, if I want to consider more broader concept, there comes analyticity or analytic function in a domain D. In the previous case, we are actually considering an independent plane, z organ plane. We are considering a point z0, and we are saying that the function is analytic at that point. So around that point, we can construct different neighborhoods, and the function is differentiable at all these points inside the neighborhood. Now, if we know that the function is analytic in the domain D, then domain means a two-dimensional region which you can consider in the organ plane. So this is domain D. So we can consider any arbitrary point here in the domain, and at all these points which are inside that domain, the function will be analytic. That means this is a point in the domain, so around that point I can construct a neighborhood where the function is differentiable. This is a point inside the domain, so around that point I can construct infinite number of neighborhoods where at each and every point the function is differentiable. So if I know that the function is differentiable in the domain, that implies that the function is not only analytic at a given point, but the function is analytic at all these points within a domain or within the given domain. So it is more broader compared to this, because here we can know that the function is analytic only at a point, but here the function is analytic at all these points within a domain. Okay, is that clear?
Yes, sir.
Then compared to this, if I want to consider more broader concept, this is called as the entire function. What do you mean by the entire function? So in the previous case, we are considering one point, then we are saying that the function is analytic at this point. The next case, we are considering one domain, and we are saying that at all these points the function is analytic which are there inside that domain. In the third case, we can consider any arbitrary complex number in the entire eigenplane. Then if a function is entire function, then it ensures that the function is differentiable at any arbitrary point within the entire set of complex numbers. That means in the in eigenplane, if I consider any arbitrary point, so the function is entire means the function will be analytic at that point. Okay, so here we are considering only one point. Here we are considering a domain, and we are saying that the function is analytic at all these points in the domain. And here we are considering actually the infinite number of points. That means entire complex point set, that means entire eigenplane, and if I pick any arbitrary complex numbers, there is the function is analytic there. So that is more broader compared to the previous two things. Okay, was that clear?
Yes, sir.
So that is the definition of analytic function. So fz is said to be analytic at a point if the function is differentiable at every point in some neighborhood of the given point z0. Similarly, if the function is analytic in a domain D, then the function is defined and differentiable at every point of D. So another term of analytic function in a domain is holomorphic in domain. Then function which is analytic in the entire complex plane are said to be the entire functions. So this is broader concept compared to the differentiability at a point. Then this is more broader compared to this, and this is the most important thing. That means if I know that the function is entire, obviously these two will be followed. Okay. Okay, so in the next class I will be discussing how to check whether a given function is analytic or not, and we will be solving the related problems. So let me take your attendance first, then I will be sharing the exam link. Rule number 1.
Yes, sir.
Two,
Present, sir.
3,
Present, sir.
4, 5,
Yes, sir.
6,
Present, sir.
7,
Present, sir.
8, 8, 9,
Yes, sir.
10,
Present, sir. Roll 10.
11,
Present, sir.
12,
Present, sir.
13,
Present, sir.
14,
Present, sir.
15,
Yes, sir.
16, 17, 8 18
Present, sir.
Present, sir.
Present, sir. 20, sir.
Okay, 20. So this is the exam code and this is the link. So just click the link and provide your full enrollment number and exam code and complete the class test. Just someone please check and let me know whether you can access it right now or not.
Yes, sir. We can access it.
Okay, thank you Sachin. So just finish the class test by 10:20. Thank you all for attending today's class. So finish the class test. I'm leaving. Thank you.